Hello. This will be a demonstration of Proposition 31 from Book 9 of Euclid's Elements, which says that if an odd number is prime to any number, it is also prime to twice that number. We're given an odd number a, which is prime to any number b. We're also given the number c, such that c is twice of b. C is double of b. What we want to prove then is that the same odd number a is also prime to this number c, which is twice of the original number b. For if they are not prime to each other, then there will be some number which measures the both of them. We'll call this the number d. So d measures both a and c. Now because the number d measures the odd number a, we know d measures a from our first step, that's how we created d, and we know of course that a is odd from our given. Then it follows that the number d is itself an odd number. For if an even number were to measure an odd number, then the odd number would ultimately have a half part, which is contrary to the definition of odd numbers. So no odd number can be measured by an even number. They are only measured by other odd numbers. So because the number d measures the odd number a, the number d itself is an odd number. But now we have that the odd number d measures the even number c. We know that d measures c from our first step, and we just learned that d is an odd number. Furthermore, we know that the number c is an even number because it has a half part, which is the number b. So c is twice the number b, then b is the half part of c, so c is even. And we also know from Proposition 9:30 that if an odd number measures an even number, it will also measure half of that same even number, so that because the odd number d measures the even number c, that same odd number d also measures half of c, which, as I said before, is the number b. So d measures b. But now we have that the number d measures both the number a and the number b. We know d measures a from our first step, and we just learned in our third step that d measures b. But if this is the case, then a and b are in fact not prime to each other, for they have some common measure, which is contrary to our given. We were given that a and b are prime to each other. And so if our numbers a and c are not prime to each other, then the number a will be both prime and not prime to the same number b, which is obviously impossible. And so we can conclude that a and c are in fact prime to each other, which is what we set out to prove, which means we're done with the proposition. Therefore, etc., Q, E, D. Fairly straightforward one. It doesn't take too much creativity to come up with an example. The odd number 3 is prime to the number 8. And so what follows from this proposition is that 3 will also be prime to 16, which is twice of 8. And you'll notice that this proposition doesn't specify whether the second number to which the odd number is prime has to be odd or even, because this proposition works either way. 3 is prime to 11, so it's also going to be prime to 22, like that. And we see that both these statements hold, so this proposition is true. We can verify that. That's all I've got to say about this one, so I'll end the video here and move on to Proposition 9:32.